Okay, so previously, we discussed how to find a Jordan form and the Jordan basis. So every matrix is similar to some Jordan form, and we wanted to find the matrix that consisting of the Jordan basis, and the Jordan basis was obtainable. Well, so if you can solve a sequence of vector equations from V1 to Vk, then these vectors are going to be the columns of your matrix M. Okay. So why are we so interested in the Jordan form? Because having a Jordan form, computation of the Jordan form in practical engineering and science, is not a really good idea because that takes too much computation, and also the algorithm. So this algorithm is not stable. So just small error in input will result in a large error, especially so when you're trying to find the Jordan form with your computer. However, in theory, so we can actually achieve many interesting ideas, interesting results from the Jordan form. So today we are going to discuss the applications of Jordan form. So especially about the matrix exponentials. So maybe so it feels like so long time ago, but we actually discussed how to find the matrix expansion of the matrix when the matrix A allows a diagonalization. So, like this. A matrix A is an n by n matrix, and the matrix exponential ETA is so n factorial t to the n over n factorial times a to the n summation, and if A allows a diagonalization, so in other words, if A is m times lambda times m inverse, and this lambda here is the n by n matrix of the diagonal, so the n by n diagonal matrix, then the matrix exponential is the same m times et of lambda times m inverse. Well, here especially this et of lambda is another exponential diagonal matrix whose diagonals are nothing but the exponential of t times the eigenvalue of A, right? If A allows diagonalization, the matrix exponential is very easy to find. But what if A is not diagonalizable? So this is the topic that we will be interested in today's lecture. Conclusion is the Jordan form of the matrix A. To discuss the matrix expansion of a non-diagonalizable matrix, first I want you to focus on this matrix N. This one looks like a K by K Jordan block, a single Jordan block, whose eigenvalue equals to 0, right? Okay. And I also believe that we have discussed this earlier, but taking the power of this matrix N increases, but raises these entries of one by one to the upper right corner. So this is a very simple computation, but if you take a square of this matrix, then we have the bunch of zeros on the diagonal and another zeros above the diagonal, and above that we have just ones on these. This is not the diagonal, but we have ones in these entries. Okay. Well, this is just merely computation. So if you cannot trust me, then you can just verify by yourself. And I also take cube of the matrix N, then these entries of 1 raises by 1. right? So now these entries are all zeros, and we have just one. We have ones over here. But number of ones, the number of entries that has one decreases by one, like this. So as you're raising the power of the matrix n, and especially if n equals if the power is k minus 1, if the power is just 1 smaller than the size of matrix n, then you're going to get a matrix whose entries are all zeros but only one. But this only one, this upper right corner equals to 1. Okay. And finally, if the power of the matrix n is greater than or equals to the size of matrix n, then you're going to get the zero. You're going to get a zero matrix. Okay. Okay. Right. And what we're going to do is we want to find the matrix exponential of this matrix n. So by definition, so you are supposed to compute this infinite series. Okay. But the thing is, this is actually not a infinite sum. This is a finite sum. Can you see why? Because so even though so as your index k is greater than or equals to k, sorry, I somehow messed the notation. Sorry. If the index k is greater than or equals to the dimension of the size of n, then this guy is going to be the zero matrix. So there is no contribution to the computation, right? So in fact, expanding this, I only have these many terms. This is a finite sum, not an infinite sum, right? So I Tn 1 over 2 factorial times t squared n squared all the way to the n to the k minus 1. And there's nothing more. So the summation must end at here. Okay. So this is a finite sum. So I won't have too much trouble in this computation. So this is the result. As a result, I have a bunch of ones on the diagonal, but these ones are coming from this identity matrix. And above this diagonal, so I have t's from here to there. And these t's are coming from this t times n, right? Because this is my n. So if you multiply t, then all these ones are now t. And taking summation, I have these t's here. And 1 over 2 factorial times 2 t squared times n squared. So this term is going to contribute these numbers, these entries. 1 over 2 times t squared over here. And finally, this last guy will contribute to this last entry on the top right corner. Okay. So this is the matrix exponential of the very special matrix n. Right? Okay. Okay. Now I want to prove something, probably the most important proposition in today's lecture. I want to prove this proposition. So A and B, suppose that A and B are the square matrices of the same size. And we are assuming that A times B is B times A. So in other words, A and B, they commute under the matrix multiplication. Then the matrix exponential of A plus B is matrix exponential of A times matrix exponential of B. So in this case, so the matrix exponential is exactly behaves like the regular exponential function as in the calculus 101. Many lectures ago, so I hope you remember this, but I tried to introduce this proposition. So E S plus T times A is ESA times ETB, TA. Do you remember this proposition? Yeah? No? We had this proposition. So even though I introduced them, I introduced this without any justification, but I strongly believe that, so I have introduced this. But it turns out this proposition in the red is very special case of that proposition, right? Because S times A and T times A, clearly they commute under matrix multiplication. So, okay, never mind. So let me prove this. First, I try to compute the matrix exponential of A times matrix exponential of B. And because of our definition, this is the matrix exponential of A, and this is the matrix exponential of B. And expanding these two parentheses, and I will write down everything in descending order. So the constant, well, not exactly constant, but the constant term is identity times identity is here. And for the linear term, so A times I and I times B appears over here. And for the quadratic terms, so 1/2 times A squared, this guy times I, and A times B, and I times 1/2 times B squared. So these are quadratic terms, and they appear in the second parenthesis. And the third, the cubic terms, I times this guy, and these are the cubic terms, and it goes on forever. Okay, but the thing is that everything is written in descending order. All right, so this is EA times EB. But on the other hand, now I try to compute E of A plus B. E of A plus B. Again, by definition, I plus A plus B, it goes on like this. And we compare this expression and that expression. And comparing the term by term, so identity is the identity, good. A plus B is A plus B, again, nice. But this guy, is this guy same as this guy? Okay, let me check this out. So A plus B squared is A plus B times A plus B. But you have to remember, this is not a multiplication to real numbers, but this is multiplication of two matrices. So A times A times B, and B times A and B squared, right? So generally speaking, so AB is not the same as BA. So I have to stop at this point. But since we are enjoying this very nice property of the commutation, so AB plus BA can now be simplified to 2 times AB. And now this expression, plugging in this expression over here and dividing everything by 1/2, now this quadratic term is the same as this quadratic term. So they are the same thing. So in other words, if you do not have this very nice property of the commutation, then this guy may not be the same as this one. And you cannot enjoy these properties. But however, so since we are assuming that A and B, they commute under the matrix multiplication, so this guy equals that. Again, obviously, so I just omitted the cubic terms and higher terms because it's just a matter of computation. But you can easily convince yourself that each of these terms they agree each other. So E to the A plus B is EA times EB. Okay, great. So therefore, if A matrices A and B commute, then the matrix exponential is exactly behaves like the regular exponential function in calculus. Okay, so why are we doing this? Because this time we will be finding a matrix exponential of a single Jordan block. Suppose that J is just a single Jordan block, not a entire complete Jordan form, but a single Jordan block. J is a single Jordan block of eigenvalue lambda size k. Then I can always decompose this single Jordan block J as a lambda times lambda times the identity matrix plus the n by n matrix n, right? Just try to imagine the picture of the k by k single Jordan block. Right? So it has a bunch of lambdas on its diagonal, and above the diagonals you have another bunch of ones, and all the other guys equals to 0. Therefore, J must be written as lambda times I plus n. Okay. Okay, and I want to compute the matrix multiplication of J, so ETJ. Matrix exponential of J, ETJ. And well, I am replacing this J by lambda I times n. So, and you know, the lambda I and the matrix n, they are commuting under the matrix multiplication. Why? Because lambda I is just some scalar multiple of the identity matrix, because identity matrix always commute to any other matrix, right? Therefore, lambda I and n, this guy and this guy, they are satisfying this condition. Therefore, in this case, matrix exponential of this guy can be broken down, factored into ET lambda I times ETN. Okay. Okay. Now, can you compute this matrix exponentials? ET lambda of the identity matrix. Matrix exponential of some scalar multiple of the identity matrix is one of the easiest one to compute. Right? So this is just simply ET lambda times the identity. So this is the because this is a diagonal function, diagonal matrix whose diagonals are all ET lambda. So this guy must be this. Okay. Okay. So this is the identity. Therefore, if you multiply this by this, then everything is just simply ET of lambda multiplied by this scalar multiplication. Okay. All right. Good. So, and we already know how to compute ET of n. So this is ETN, right? This is our ETN. And all I have to do is just take a scalar multiplication of ET lambda to the left. So each of these entries must be multiplied by ET of lambda. And this is what you get. So we had a bunch of ones on the diagonals, but these ones are now changed to ET lambda. And we had all the t's above the diagonals, but these t's are now t times t lambda, and so on, like this, all the way to this corner. Okay. So this is how you compute the matrix exponential of a single Jordan block. Right? Right? Yeah, I know. So it sounds very scary. So I feel like I'm spitting out too many theories in a limited time. But well, I believe you can easily read the pattern from this matrix, right? So there's a bunch of t's and a bunch of exponentials and t times exponential 1 over 2 times t squared times exponentials, and the pattern of this matrix is very easy to follow, I think. Okay. Just try to, well, not hard to memorize. Well, I really hate to say you have to memorize this, but well, there's actually nothing to memorize, because as long as you understand the pattern, then everything is very straightforward. Okay, good. So now, let me turn to a more general case. This time, suppose that my Jordan form J consisting of multiple Jordan blocks from J1 to JL. So, well, I have a diagonal. This is a diagonal block matrices, and each of these blocks are the Jordan blocks from J1 to JL. So suppose that this Jordan form J is a Jordan form consisting of L Jordan blocks, yeah. And what is the matrix exponential of this guy? So I try to compute the matrix exponential of this Jordan form J. Then ETJ is another block diagonal matrix whose blocks are the matrix exponentials of each of these Jordan blocks from J1 to JL. So since this is J1, so this first block is ET of J1 and da da da, and this is ET of JL, right? This one should be something. So this is very obvious. This one must be. So finally, if J is the Jordan form of the matrix A, then you must be able to find a Jordan basis matrix M here and there. So A is M times J times M inverse, and well, the matrix of matrix exponential of this matrix A is well, by definition, summation of t to the k over k factorial times a to the k. But this a to the k can be replaced by m times jk times m inverse, and kicking out this m and m inverse out of this summation. So this is what you get. This is the matrix exponential of the Jordan form, and this is and you can compute this from this algorithm. So this is going to be your matrix exponential of the matrix, possibly non-diagonalizable matrix A. So this is how you take the matrix exponential of non-diagonalizable matrix. Okay. I mean, the point is you consider its Jordan form and take a matrix exponential of the Jordan form, and that's it. And you take a similar transformation. All right. Yeah, I feel like I spelled out too many theories. So why don't you just turn to some more concrete example? Oh, by the way, so I uploaded this lecture note in the PRMS. So, well, maybe you don't need to spend too much time taking note. If needed, then why don't you just download it from the internet? All right, so I want to solve this system of differential equations. So this system consists of two equations, U1 and U2. Also, I am looking for a solution that is satisfying this initial condition. Okay, so well, idea is very simple. I have a system of equations and the initial condition. Therefore, the solution of this system is the matrix exponential of this guy times the initial condition. That is the solution, right? Okay. So the thing is, what is the matrix exponential of this guy? Well, I'm going to call this guy A. In order to find the matrix exponential of this matrix, then first you will try to find a eigenvectors and eigenvalue of this matrix. And to find them, and first I will begin from the characteristic polynomial of this matrix. So 2 minus lambda times minus lambda minus 1 times 1. So, well, simplifying, this is going to be your characteristic polynomial. Yeah, so it has eigenvalue 1 and whose algebraic multiplicity is 2. So, since I found the eigenvalues, so let me try to find its eigenvector. So, I subtract all these diagonal entries by eigenvalue 1. So 1 minus I and 1 minus I, and x and y equals to 0. So, well, so it means x minus y equals to 0. So this is, well, I can find only one linearly independent eigenvector. So simply I will say just 1 and 1. Okay. So therefore, this eigenspace E of lambda is spanned by this guy. So, so that means the geometric multiplicity of eigenvalue 1 is 1, which is 1 less than the is algebraic multiplicity. Therefore, this matrix does not allow diagonalization. Okay. Okay, great. So, can you guess this Jordan form of the matrix A? It has eigenvalue 1 and its algebraic multiplicity is 2 and geometric multiplicity is 1. And you know, geometric multiplicity is always the same as the number of Jordan blocks. Since its geometric multiplicity is 1, therefore its Jordan form must have just one single Jordan block, right? And whose size must be 2. Therefore, and how many such Jordan forms can you find? There is only one such Jordan form, which is this guy, right? So this one must be the Jordan form of the matrix A. Okay, great. If you can follow up to this point, which is very nice. And what I want to do is, I want to find the Jordan basis of this guy. And how do you find the Jordan basis? And you are supposed to solve the sequence of vector equations. And we have already found V1. What is V1? V1 is just nothing but the eigenvector of eigenvalue 1, right? And so it is okay to say, it is okay to declare this guy to be my V1. So let me say this guy is my V1, okay? And I will need to solve the second equation. And I want to find this vector V2, satisfying this equality. So A minus lambda I, which is this, and this is my V2, is equals to V1. This is my V1. I'm just simply plugging in this guy to the right-hand side. Okay. And, well, it turns out x minus y is 1. So in principle, every x and y satisfying this relation will be your vector V2. Okay, but for simplicity, there is no reason to stick to a complicated number. So I will just say x equals to 1 and y 0. Good? So this guy is going to be my V1. Okay? Okay. Now, I am ready to find out my Jordan basis matrix M. My Jordan basis matrix M is a 2x2 matrix whose first column is the eigenvector V1 and the second column is V2. So this guy, vector V1, is on the first column and vector V2 goes to the second column. Okay. So 1, 1, 1, 0. So this is my M. So, so therefore, I found the Jordan form and the Jordan basis of the matrix A. So now I'm ready to compute the matrix exponential of this matrix A. So ETA is M times ETJ times M inverse. And this is my M. And well, taking the inverse of the 2x2 matrix, 2x2 matrix is easy. So, well, this is the M inverse. And what is the matrix in the middle? The matrix in the middle is ETJ. And but since this is my J, therefore ETJ is ET, ET, and T times ET, right? So this one's supposed to be your matrix exponential of this non-diagonal algebra matrix. Do you think you can do this? Well, yeah. As a beginner, so all this computation looks somehow very complicated. But, well, I must agree that the computation itself is very somehow complicated. But all these theories, they are actually doable in some sense. So, and well, I told you in the exam, so there won't be problems involving find the Jordan form of the Jordan basis of the maybe 4x4 matrices. So probably this is the hardest problem that you can ever find in your final exam regarding the Jordan basis, especially Jordan. Well, maybe there can be some problems of determining a Jordan form of 4x4 matrix, but you are not asked to find the Jordan basis of the 4x4 matrix. So in terms of the Jordan basis, then this is what you're gonna do. And I believe this is somehow doable computation. Yeah? No? Anyway, so this is the matrix exponential. Okay, now I can finally solve this initial value problem. The solution of this system of equations, differential equations, is matrix exponential of A times the initial condition. And this is my matrix exponential. And what is my initial condition then? This is my initial condition. So I simply plugging in, multiplying this guy on the right of this matrix exponentials. And all you have to do is just some tedious computation. And it turns out e to the t times t plus 1 and t. So this is going to be your answer, solution. Okay. Good. Well, if you're not that familiar with, if you don't think you're not, if you think you're not that familiar with this kind of computation, but I believe this is just a matter of working out. So just you can spend like a couple of times. Maybe you can spend, well, maybe 20 minutes or 30 minutes in working out these exercises of small dimensions. Then I guess you can easily get the point of this matrix exponentials. Yeah, hopefully. There is another very important proposition. I'm going to give you a couple of seconds to read the statement. It says like this: I have a square matrix A, which is not necessarily diagonally eligible. Then determinant of the matrix exponential is this exponential on the right is the regular exponential in calculus 101, followed by the trace of the matrix A. I believe I have proved very similar propositions maybe a couple of lectures ago, but that proposition was about the case when A allows a diagonalization, right? So the proposition was like, if A allows diagonalization, then determinant of the matrix exponential is the exponential of the trace of A. But this time around, we are actually dropping the condition that A allows diagonalization. So that means this very nice equality is even true when your matrix A is not diagonalizable. Okay? So how do I prove this? Well, I can also prove, well, the idea is also the Jordan form of the matrix, right? So in such case, well, in such propositions, the Jordan form plays a very crucial role. Well, you know, every matrix is similar to some Jordan form. So A is m times j times n inverse. So, well, in this schematic picture, so A is m times this block diagonal matrix times m inverse. And I am trying to take an exponential matrix exponential of this matrix. Taking the matrix exponentials, then it's going to be m times E matrix EJ1 EJL. These guys are going to be the block diagonals of this middle matrix. Okay. And what now? Now I am trying to compute the determinant of this guy. But you know, the determinant is invariant under the similarity transformation. So determinant of this matrix is the same as the determinant of the matrix in the middle. Okay. And the thing is, this matrix, this is a block diagonal matrix. And how do you find the the determinant of the block diagonal matrix? The determinant is a determinant of each of these blocks and taking product. Right? So this is how you compute the determinant of the block diagonal matrix. You compute the determinant of each of these blocks and you multiply them all together. Okay? So determinant of this guy times this guy, determinant of this guy. And you take the product. Okay. But this is also, each of these blocks, they are also upper triangular matrix. Right? This is an, well, for example, this is an upper triangular matrix. Why? Because this was the ETJ. This is clearly upper triangular matrix, right? The matrix expansion of a single Jordan block is upper triangular matrix. And if your matrix is an upper triangular matrix, then its determinant is going to be the product of all its diagonal entries, right? And if you take the product of this, then that is going to be the exponential of the summation of all its diagonal entries, sum of all eigenvalues, right? Same is true for this and same is true for that. So therefore, multiplying all together, you will get the e to the summation of all eigenvalues of this middle matrix, this matrix J. Right? Taking up the multiplicities. So this summation of lambda i's means summation of all diagonal entries from here to there, right? But do you know that? Do you remember this? Well, every k by k, well, every n by n matrix has taking, well, counting up the multiplicities, every n by n matrix has n eigenvalues, right? And if you take the sum of all these n eigenvalues, then that is going to be the trace of your matrix. Right? And here, I am trying to take a summation of all the eigenvalues of the matrix J, the middle matrix. So this is the trace of the matrix J. Right? But again, the trace is also invariant under the similarity transformations. So that means if two matrices are similar to each other, then their traces also must agree. So, and this middle matrix J and the matrix A, they are similar to each other. Therefore, trace of J is the same as the trace of A. Okay, so determinant of EA is exponential of the trace of A. Right? So this very nice and beautiful identity again holds for non-diagonalizable matrix. So determinant and exponentials, they are commuting like this. So determinant and matrix exponentials, once they commute, determinant is going to be the trace. Okay. Great. So this is how you prove this such a nice identity, such a nice theorem. All right. So this is the end of chapter 5. Now we are turning to next chapter, chapter 6. Before I begin chapter 6, so I also need to mention this. In chapter 5, we implicitly assume that every matrix in chapter 5 is complex matrix, right? Even though your matrix A has all real entries, but your eigenvalue can be some complex number. Therefore, there always is some possibility that you are dealing with some complex matrix. So in chapter 5, so our basic idea was that everything is a complex matrix, but in the chapter 6, now we are returning to the world of the real matrix. Every matrix that appears in chapter 6 is, well, unless otherwise mentioned, then you should consider the matrix is a real matrix, matrix of the real entries. And so we're going to talk about the positive definite matrix. So what is the positive definite matrix? So in order to give you the proper idea of the proper motivation of the positive definite matrix, then I cannot avoid mentioning the Taylor series of the multivariable function. I'm really sorry for this, but well, have you ever attended? So have you attended the multivariable calculus course before? Maybe yes, maybe no. But if you have attended the multivariable calculus course, then that is great. But if you haven't, but technically that doesn't make too much problem because, well, understanding multivariable calculus will help you motivate the study of the positive definite matrix. But even if you don't, but that's fine. You can still follow the definitions. That's okay. So don't worry about it too much. All right, but I will begin from the study of the two variable differentiable functions. I have a function f, so whose domain is in some open subset of the two-dimensional Euclidean space R2, and whose codomain is just some real number. So this is a we say this is a two variable real values function from U to R. And well, also we are assuming that f is a differentiable function. And you know, every two variable function, every graph of the two variable function can be drawn in drawn as a surface in three-dimensional spaces. Just like this. Yeah. Last night I tried my best to draw the nice, pretty picture. So let me say this is the picture of the graph of this function. And we are assuming that f has a local maximum or local minimum at this point in the domain of function f. You know what I mean by local maximum and local minimum. A point is called the local maximum if you can find an open neighborhood of the point so that in that neighborhood you cannot find any point whose function value is greater than the function value at the point of interest, then that's going to be the local maximum, and the local minimum goes like the similar. And suppose that f has a local maximum or local minimum at this point. And I claim that in this case, the partial derivative of f at this point must be 0. So partial derivative of f with respect to x equals to 0, and partial derivative of f with respect to y also equals to 0. Why is that? To explain this, so this guy equals to 0. So it has a local maximum. In this picture, it has the local maximum at AB. So that means there is a mountain peak over here. And just consider the section of this graph along with the plane that is parallel to YZ plane. So YZ plane. Then if you take such a section, then the curve of the intersection is going to have the local maximum at this point. This light green line, light green curve represent the curve of intersection. And this curve of intersection clearly has the local maximum at this point. Therefore, f partial y at AB should be 0. And likewise, if you take a section of this graph along with the plane that is parallel to XZ plane, then this heavy green curve will going to represent the curve of intersection. And clearly this curve of intersection has a local maximum at this point. Therefore, this partial derivative also must be 0. Okay. So I mean, the point is, if you can find local maximum, local minimum, and their partial derivative equals to 0. Okay. Okay, great. Now things are getting somehow complicated. We are interested in the Taylor expansion of the multivariable function. Do you remember the Taylor expansion? Yeah, probably. So I guess you can remember the definition of the Taylor expansion of the one variable function. What about the Taylor expansion of the two variable function? Well, I will not try to explain the Taylor expansion of the multivariable function, but well, I can just simply say the Taylor expansion is some constant function value at this point and partial derivative at this point multiplied by h1 and h2 and all possible second derivatives times h1 squared and h1 h2 and h squared and everything divided by 2. So and so on. So this is a Taylor expansion. And we are assuming that h1 and h2 they are sufficiently small numbers. So there will be some higher order terms that will be depending on the h1 and h2. But since we are assuming that h1 and h2 are very small numbers, therefore small numbers raised to the higher power is almost negligible. Therefore, we can simply ignore them. So I can simply say the behavior of the function f near the point AB is completely determined by this quadratic function, the polynomial of h1 and h2 with degree 2, right? So this polynomial is well, and these numbers, they are just some fixed numbers, right? So this is just polynomial of variable h1 and h2, and this polynomial will determine the behavior of the function f at near AB. And moreover, we are assuming that this guy and this guy equal to 0. Because of the reason. Because the function has a local maximum or minimum here. So this guy equals to 0. So simply speaking, the function behavior near A and B is determined by some constant plus a polynomial of degree 2 functions. This polynomial will be called a quadratic polynomial. Okay, so this polynomial actually governs the behavior of the function. Okay, so the question is, so therefore, in order to study the behavior of the function, then we actually need to study this polynomial of degree 2. So we gave very interesting name to this polynomial. So this is the definition. A quadratic polynomial Q. So this quadratic polynomial is is consisting of only degree 2 terms, ax squared 2 times bxy plus cy squared. And this quadratic polynomial is called positive definite. If it's satisfying these two conditions. Okay, so what are these? You must be able to see that these quadratic polynomials, this quadratic polynomial can be considered as a two-variable function, right? A function depending on the x and y. And this quadratic polynomial equals to 0 when x and y equals to 0. When x and y, they are both to 0, right? So this is a trivial zeros of this function q. But in order to be positive definite, and this x, well, this is the only possible option, being that qxy equals to 0. So that means if x and y are some non-trivial vector, then the function value of q is always strictly positive. The function value of q can attain 0 only if when x and y equals to 0. If this polynomial q satisfying these two, then we say this polynomial is positive definite. Okay. So I tried to draw a silly picture. Well, so if you do not get the clear idea of the being a positive definite quadratic polynomial, then why don't you just try to draw the graph of this guy, this function? So this is the graph of v equals to qxy, right? And in order to be positive definite, the only possible graph of the positive definite polynomial is going to be something looks like this, right? So this looks like some ball, and it only touches the xy plane at the origin. And if deviating from the origin, the function value always must be positive, right? This is the graph of this is the typical graph of the quadratic. This is the typical graph of the positive definite quadratic polynomial. Right. Yeah. Also, a quadratic polynomial is called negative definite if minus qxy is positive definite. This definition is very silly, but this is also easy to understand. Negative definite means the graph of a negative definite polynomial always looks like this, right? So this is like inverted ball that only touches the xy plane at the origin. And otherwise, when x and y is not 0, then the function value of negative definite quadratic polynomial is always strictly negative, right? That is negative definite polynomial. Great. So how do you know that any given quadratic two-variable function? How do you know any given quadratic two-variable polynomial is positive definite? This is very interesting question. And the next lemma tells us very useful criteria to determine that positive definiteness of the two-variable quadratic polynomial. So I have two-variable quadratic polynomial, and this guy is positive definite if and only if AC is greater than B squared and A is positive. Okay. Hey, hold on. This expression is somehow very familiar to me. What is this? Can you recognize this? This is the discriminant of the quadratic polynomial. This 판별식. This is the discriminant of the quadratic polynomial, right? So that, in other words, this two-variable quadratic polynomial is positive definite if and only if the leading coefficient is positive and the discriminant is negative, right? Okay, so let me prove this. Okay, suppose that, okay, this direction first. Suppose that Q is positive definite. In order to be positive definite, then I believe that A must be always positive. A has to be positive, right? Why? Because suppose that if A equals to 0 or A is some strictly negative number, then in that case, you can actually find some non-trivial choice of x and y so that your function value qxy is strictly negative, right? Because of that reason, so A always must be positive. Good. Okay. So what I'm gonna do from now on is I'm gonna apply the trick of the completing the square. So what is completing the square? So I factor everything with the leading coefficient. So I'm gonna divide those guys by A. And x squared plus A 2b over A times xy, and 1 over 2 times of this, and take a square, which is this. And since I added this guy and I subtract the same guy over here, and combined by c times y squared, this is going to be my second term, right? And as you can recognize, this the first term, first parenthesis over here is a perfect square. So you can factorize them like this, plus this guy. And in order this guy to be positive, and this is always non-negative number, and this is positive, and okay, and in order to be positive definite, this is always non-negative, so this guy always must be positive, right? So in order to be positive definite, that this guy also must be positive, and which is this condition. But summarizing, well, simplifying this, so I have this relation. I have this inequality. The other implication, other direction of the implication can be proved in a similar way. So I will omit this. But you know, I guess you got the idea. So this is the criteria. All right. So and applying the same trick, so I can prove the same thing. So any quadratic polynomial of two variables is negative definite if and only if the leading coefficient is negative and the discriminant is negative. Well, I'm not going to bother to prove this corollary. So you can easily do this. Also, I want to introduce the notion of the semi-definite quadratic polynomial. Semi-definiteness is somehow relaxed condition compared to the positive definite polynomials. So let me follow the definition. I have a quadratic polynomial of two variables, x and y, and we say this guy is positive semi-definite if so function value of qxy is greater than or equals to 0 for all xy, and qxy equals to 0 for some non-trivial x and y. If you can find such an x and y, then we say the function is positive semi-definite. Can you think of any nice example of the positive semi-definite polynomials? Maybe like this. X minus y squared. This is clearly not a positive definite polynomial, right? Because if suppose that if x equals to 1 and y equals to 1, then this guy equals to 0, right? So this is clearly not a positive definite, but this is still positive semi-definite, right? The function value is always greater than or equals to 0, and well, if x and y value both equals to 1, then this guy is 0. So this is positive semi-definite. So in terms of the graph, the typical graph of the positive semi-definite polynomial will look like this. Right? Like, and negative definite goes almost like so, almost analogous way. So a quadratic polynomial is negative semi-definite if function value is always less than equals to 0, and if you can find some non-trivial x and y that makes your function value equals to 0. So typical graph of the negative semi-definite polynomial will look like that. You get the point. I guess you get the point. Okay. What about saddle? A quadratic polynomial is saddle if it attains both positive and negative function values. So in picture, its graph must be typically something like that. Okay. Well, this is the origin, and if you deviate from the origin in some certain direction, then your function value should be negative. But if you deviate your function in this direction from the origin, in this direction, then your function value might be positive. So, for instance, like x squared and y squared, this is saddle, right? So for some clever choices, the function value can be positive, and your function value also can be negative. So, well, the idea is very simple. So in order to be quadratic polynomial, your discriminant must be quadratic or negative definite polynomial. Then your discriminant must be negative. But if your quadratic polynomial is saddle, that means you can actually factorize your polynomial into two real linear factors. If such a real factorization is possible, then your function is saddle. Then your quadratic polynomial is saddle. But if such a real factorization is not possible, then your polynomial should be either positive or negative definite polynomials. Okay. So all about the factorization, real factorization. Okay, sorry. I'll just get rid of these silly pictures. I really don't like them. Summarizing everything that I have said so far. So if discriminant is less than or equal to 0 and leading coefficient is positive, then Q is positive definite. Positive semi-definite. And if the discriminant is less than or equals to 0 and leading coefficient is negative, then Q is negative semi-definite. And if your discriminant is greater than or equals to 0, then Q must be saddle. Okay. All right. Okay. So I have spent a lot of time in discussing quadratic polynomials. You might be wondering, what is this anything to do with the linear algebra? Yeah. So clearly there is a way to associate any given quadratic polynomial in the world of the matrix, just like this. So I have this. This is a quadratic polynomial of two variables, but we can consider it as this 1/2 row vector times 2/2 vector matrix times 2/1 column vector. In dimension wise, the resulting guy should be just 1/1, just a 1/1 matrix, which is just a number. And so this is a number. This is just a number. So they agree. And so I try to multiply these matrices. So this guy just carries over, and I multiply this and that. Then this is xy times ax plus by and bx plus cy, and this guy times this, and this guy times that. I have this, but I can see two the same terms over here and there, and combining these two, I end up this. So this is how you associate any given quadratic polynomial of degree 2, quadratic polynomial of two variables to a 2x2 matrix. So all the information on this quadratic polynomial is contained in this 2x2 matrix. Okay. And this 2x2 matrix is a real matrix, which is very obvious. And more importantly, this matrix is a symmetric matrix. Right? A, C, but these two entries are the same. So the point is, the idea is every I messed up. Every quadratic two-variable polynomial can be associated to 2x2 real symmetric matrix, and vice versa. And so this guy is positive definite, means, well, let me just name this guy to be my x and this guy to be a. This guy is positive definite, means this equation, this matrix is greater than or equals to 0 for all two-dimensional vector x, and this guy equals to 0 only if x is the 0 vector. Right? So a quadratic polynomial being positive definite, this condition can be translated like this, using the terminology of the linear algebra. So, okay, finally, I can give you the definition of the positive definiteness of the real symmetric matrix. Suppose that A is a real symmetric matrix. A is positive definite if x transpose times A times x is greater than or equals to greater than 0 for all non-zero vector x. Well, if x equals to 0 vector, then this guy is equals to 0. Okay, clear, obviously. But if this number is greater than 0 for all non-zero x, then we say this matrix is a positive definite. And also there is notion of the negative definite if this guy is minus of a is positive definite. You have to remember, so you should be able to see that the definition of positive definiteness is not only for 2x2 real symmetric matrix, but this definition is for any n by n real symmetric matrix. Right? So x1, x2, xn, a11, a12, a1n. Usually it has to be a21, but since this is symmetric, I will say a12. So this is xt times xt times a times x. So now this is somehow hard to see, but I claim that this is still a quadratic polynomial of degree 2, right? Whose variables are not x and y, but x1, x2, xn. So this is a quadratic polynomial of n variables, right? A quadratic polynomial of n variables can be associated to this n by n real symmetric matrix. Okay. And so therefore, we can discuss the positive definiteness or negative definiteness of any real symmetric matrix. Okay. Okay. I will be turning to the Taylor multivariable calculus. Suppose that I have, so we will discuss the tailored expansion of degree 2. F is a twice continuously differentiable function, and P is the point of interest, and H is just a small vector. Then we are interested in the function value of f of P plus H. And according to the theory of the Taylor series of multivariable function, then this guy can be approximated by the function value at P plus the linear terms. So these are all numbers times HI, and 1/2 times all possible second derivatives of F at P times HI and HJ. So this is the degree 2 Taylor polynomial of this n variable function, right? This is not a 2 variable function anymore. This is the n variable function, right? And so then this is this approximation. If H is very close to, if H is close to 0, then the function value at P plus H is determined by this degree 2 polynomial. This is polynomial of variable from H1 to Hn, right? But suppose that F has a critical point at P. So in other words, suppose that F has a local maximum or local minimum at point P. Then this first partial derivative equals to 0 for all I. Therefore, all these guys equals to 0. So the second linear term vanishes. So f of the function value, when function value of f at P plus H is this constant plus this degree 2 terms, degree 2 polynomial, right? So as I said, this function f has a local maximum or local minimum at P. But how do you know it is local maximum or local minimum? So all the crucial information to determine the local maximum or local minimum of f is contained in this quadratic polynomial over here, right? Because this is constant, so it doesn't affect too much. So this is a quadratic polynomial. So each of the quadratic polynomial of variables from H1 to Hn, then this guy can be written as using matrices. This 1/2 just carries over here, and this matrix in the middle is contains all possible partial derivatives. So this guy times this guy times this is going to be will be the first term that appears in this summation, and this guy times that is going to be maybe the second term that appears in the summation, and so on. So I strongly recommend you to try this by yourself. Suppose, just say n is 4. Just choose some reasonably small number 4, but not too small. Just say n equals to 4. Then just try to write down everything in this summation. Then you should be able to get the 16 different terms, right? And also you write down this matrix matrix multiplication. Then you should be able to see that this guy is precisely the same as this one. And just one more thing. I always forget this guy's name, but what was the Clarios theorem? So the Clarios theorem says that when you try taking the higher partial derivatives of a function, then the order of the derivatives actually doesn't matter. The partial xy is always in the partial yx, right? And so on. So that means this matrix in the middle is n by n matrix, real n by n real matrix, and this is a symmetric matrix, right? This guy is the same as this one. and this guy same as this one, and this guy, well, same as this, right? So this is a real symmetric matrix, and this is we say this Hessian of F at P. So I will say this is 1/2 just carries over, and H transpose times A, this matrix A is the Hessian of F at P, and H over there. And the idea is, if this matrix, if this middle matrix, if this Hessian of F at P is positive definite, then this guy is always positive for non-zero H, right? Therefore, comparing this guy and this guy is always greater than this one. If Hessian is positive definite, then that means the F of P is local minimum, right? Because Fp plus H is always greater than Fp. On the other hand, if this guy is negative definite, then this guy is almost always negative, right? Therefore, this guy is always smaller than this number. Therefore, this is local maximum, right? So being local maximum or being local minimum is determined by positive or negative definiteness of this Hessian matrix. So the natural question arises: how do you determine any given n by n symmetric matrix positive or negative definite? That question is answered in the next lecture. Okay, thank you for your patience and see you next time.